Hi everyone, I'm Arnav from Mysten Labs, and I'm excited to talk about our work on zk Authenticator for blockchain. This is, oh, sorry about that. I was kind of moving around, sorry. So this is joint work with my Mysten colleagues, Kostas, Deepak, Joy, and our intern over the summer, Ayush from GMU. So let me first delve into why this problem is interesting. So blockchain today is a wonderful medium when it comes to transparency. All the transactions are visible on the blockchain, and you can understand what's going on in each transaction. Transaction details are visible, participant identities are visible. And crucially, the authentication logic is also visible. And this may not be desirable in many circumstances. So for example, let's say you are interacting with your family and you want to delegate some authentication policy to your cousins, your brothers and sisters, and you want to do some private transactions on the web, where you don't want to disclose what kind of transactions they are, right? Or imagine that you go on a camping trip with your friends and you are settling your rentals, expenses. All of those transactions will be visible on the web if you are doing it over a public blockchain. And it's not only that, it's not only potentially embarrassing, these transaction details, but it could be a security risk as well. So imagine a corporate scenario. So there is a corporate treasury transaction scenario here, where let's say there is a public policy that to sign off on transactions that are more than $1 million, you need 2 of 3 signatures from the CEO, CFO, or CTO, all right? And 1 of 3 for less than $1 million, okay? So and what an attacker could do is like, by looking at this transaction structure, they could say, okay, I need 2 signatures for $5 million. I can focus on the 2 weakest accounts, okay? And the attacker may know that Carol, being the CTO, is kind of the strongest technically. So presumably, they'll focus their attack on Alice and Bob, ignore Carol, and be able to do, with various strategies that they can think of, be able to profit from looking at this transaction structure, okay? So essentially, the point is the attackers can optimize their strategy because the transaction structure is visible, okay? So what's the current landscape right now? So there is a privacy expressiveness trade-off right now. So you have threshold signature schemes where you can get signer privacy for a limited expressivity of transaction structures. So essentially, these are compact signatures. These are efficient to construct. But the logic is pretty simple sometimes, okay? You could do these through smart contracts, where you can do arbitrarily complex logic. But the inputs are public. The policies are, again, public, okay? So there is a trade-off between privacy and expressiveness here. So next, you could think, like, why not just apply zk and this is solved, right? But the problem is that, okay, zk can handle arbitrarily complex logic. The inputs are private, but the policies are still public, all right? So this doesn't quite solve this problem. So let me delve a bit deeper into why this is the case. Okay, so imagine how you would deploy zkPs as an authentication mechanism for transaction privacy, right? So imagine there is a policy somewhere, okay? The admin of this policy generates the proving key, the verification key, gives the proving key to the transactor, okay? So this is some delegated person who is allowed to transact, okay? And let's bind the address to the verification key of the zk proof, okay? So that's the address. And the zkVK is public. Now, Alice, who knows the zkPK, the proving key of the circuit, can post a transaction which satisfies this policy directly on the chain, and then validators can verify just the zk proof to authenticate the transaction for this address. So since the validators know the verification key of the zkP, they can just use the transaction as a public statement and verify that against the verification key. What's the problem with this? The problem is that there is no guarantee that this zkVK doesn't reveal the policy itself, okay? This is not formally expressed in previous literature. So what we come up with is a scheme called zkAt, Zero Knowledge Authenticator, with policy privacy. So what this gives us is we claim that this is the first solution to achieve both policy privacy and expressiveness. So the key technical contributions we make are fourfolds. I'll go into a bit of detail into each of them, but maybe not too much today. So we formalize this goal of hiding the policy itself by what's visible on the chain. We construct a policy private zkAt from a simple modification of growth 16 using a property called VK equivocation. We construct an even more powerful primitive called zkAt plus, which gives you something called oblivious updates. And what oblivious updates means that you can actually even change the policy behind the curtains without anything being visible on the chain, okay? And this gives security guarantees to the policy admin without any on-chain footprint. So this is another layer of privacy beyond even policy privacy. We also did some practical experiments, and our early results are promising. Okay, so let's now see how this policy private zk authenticator would work. The setup is the same as before. So again, the policy admin generates this CRS, which is a zk proving key, zk verification key. The zk verification key, again, is bound to the address. The validators validate transactions using the zkVK. But now, compared to the previous situation, this on-chain footprint, which is the zkVK, no longer is bound to the policy itself, and provably so. So we prove that the zkVK reveals nothing about the policy itself. How do we do that? So this is, first of all, the formalization of this property, presented in an informal way, but essentially this is what it is. So imagine standard growth 16, which is a popular zk snark proof system. How it proceeds is that it takes a policy as a circuit and generates a proving key and a verification key, okay? And for growth 16, there is no proof that this VK does not reveal anything about the policy. What we do for zkAt is we do the standard thing of generating PKs and VKs, but our setup is different, okay? So we prove that, in fact, we can generate the same VK from two different circuits, which means that by just looking at the VK, it is no longer now possible to distinguish, even if the adversary knows which two circuits it's comparing. So the adversary may have, like, we give the adversary the power to generate these circuits, actually. So the adversary generates these circuits, then asks for VK for one of them. It doesn't know which one. And even if they know the VK, still then they are not able to distinguish which circuit it belongs to. All right? And the way we would achieve this is through this technique called VK equivocation. So I'll go a little bit deeper now into how this is achieved for growth 16. Okay, so many of you, especially who are knowledgeable about zk, will know about R1CS. So R1CS is a particular encoding of circuits that is useful for zk snarks. Essentially, what it does is layers circuits into a sequence of multiplications, okay? So you have a matrix. So the circuit is essentially expressed as 3 matrices, U, V, and W. And then the circuit is satisfied if you can demonstrate a vector A such that UA entry-wise product with VA gives you WA, okay? So how this proceeds? So let's say you have an equation like, z equals x squared plus 5, okay? And for a particular value, let's say z equals 9, you want to show that there is some solution to this system, okay? And the prover has such a solution. So x equals 2 actually gives you such a solution because x squared plus 5 is 9 in that case. So how this translates to R1CS is that you would lay out the circuit evaluation of this x squared plus 5 circuit, starting from x and going all the way through to z, okay? So the first row essentially encodes that there is, so there is an auxiliary variable y, which is just the square of x. So y equals x squared, and then z equals y plus 5. So these two equations together give you the final equation, right? So the first row of this R1CS encodes the fact that y equals x squared, and the second row encodes the fact that z equals y plus 5, okay? And the quantity in green is the public element. So that element, 9, is known to everyone. But the entries which are not green, that may not be known publicly, but it is known to the prover, okay? So that's roughly how R1CS works. And this is how growth 16 takes advantage of this structure. So essentially what it does is that it translates each of the columns of these R1CS matrices into polynomials, okay? So for column 1, for example, you have U1x. For the x column, you have Ux of x, and so on. So each column of R1CS is converted into a polynomial by interpolating each entry at a fixed coordinate, okay? So you have these bunch of polynomials. So when given a witness vector 1, 2, 4, 9 as on the slide, you essentially translate that into a polynomial equation. And that polynomial equation, if the circuit is actually satisfied, that polynomial, whatever holds for each row, would also be satisfied by the polynomial, modulo a polynomial which is actually 0 at all these rows, okay? So that's what growth 16 leverages. So essentially, it now samples a secret point tau and evaluates these polynomial equations at that secret point tau and verifies that all these equations hold at the secret point tau, okay? Now, the crucial thing to observe is that whatever is needed for the verification key are particular evaluations of these polynomials at the point tau, okay? So not all of these polynomials are visible to the verification key or need to be visible to the verification key. So how we can leverage this fact is that we can now essentially increase the number of points by 1 and fix the value of these polynomials at this point tau, whereas interpolating all of these polynomials for all the coordinates, okay? So essentially what we did is just went to a dimension which is 1 higher, planted a secret, and made the verification key exactly same for whatever circuit we are given. So that's essentially the trick, which makes the verification key exactly the same, whatever circuit you are given. Okay, so going quickly, there is a drawback of zkAt, which is that you can only give one proving key like that to an adversary, because if you give two proving keys, then there are too many polynomial equations that the adversary gets, and they can solve it and recover tau, and that affects the soundness of the proof system. But we construct another system called zkAt plus using recursive snarks, which also addresses this issue. So what zkAt plus gives you is the ability to give multiple verification keys without interfering with the soundness of these proofs. Okay, and the way it proceeds is actually pretty simple. So let's say the policy admin has a signature public key, PK. Now, given a circuit, it generates standard zk proving key, zk verification key. It signs the zkVK with its public key and gets a signature on the verification key. Now, what the prover does is that, given a statement X, this prover generates first a proof pi with zkPK, okay, and then generates a proof that they know pi, zkVK, and svk, such that this x comma pi actually verifies with zkVK, and the signature also verifies. So essentially what they did was, there is an inner layer of zk which actually knows the circuit and essentially proves that the prover is able to prove with respect to that, but the outer layer actually takes this zk as its witness. So that's why, by looking at the outer layer, you do not know what policy was applied. Okay, so this is the recursive construction. And what this gives you is something very interesting. Now, you can give different proving keys to different delegated parties, but have the same verification key on chain. So essentially, think of a corporate hierarchy where you give different verification keys to different people, but they can transact on the same address. And you as an admin would still have soundness. That is, you have the guarantee that each one followed their respective policies. So we did some evaluation of the recursive snark especially. So again, a simple signature policy, like 1 of 3 signatures for less than 1K, 2 of 3 signatures else. And got decent numbers, not as fast as threshold signatures, but still sub-second efficiency. For the equivocation-based zkAt, it's interesting to note that proving and verification times are very similar to Growth 16 because it's essentially like just increasing the dimension of the co-op by 1. And the verification is also backward compatible with standard Growth 16. So given that it's already compatible with blockchains that support Growth 16 verification. Yeah, so thank you. And the paper, this is the full paper on the web, apart from the AFT proceedings, and would be glad to take questions.
We have time for one quick question. Okay, I have a quick question. So from the achievability standpoint, if you don't care about the practicality at all, this would be achievable by any zk snark if you run a universal circuit, right, and then input your policy as input to that circuit, right? But right, what you're achieving is essentially like a practical version.
Right. So we achieved exactly. So what you are saying is essentially similar to the recursive snark construction, but the equivocation one is actually comparable to Growth 16. So Yes, it is like theoretically, it was theoretically possible even before, but now we made it practical.
Nice, very nice. Yeah, let's thank the speaker again. And